report is on this surface rupture from this big earthquake, a magnitude 7.8 earthquake in 1911 in Central Asia. And the point is, it's kind of talking about intraplate earthquakes. So here it is, this place here in Central Asia. The shortening is still coming from the India-Eurasia collision. So even though it's more than 1,000 kilometers from the collision, there's still internal deformation in the continent. And here you can see all the seismicity of this mountain range called the Tian Shan. And the yellow shows the instrumental earthquakes, so ones recorded by instruments. And you see there's a lot of them in the south, along that side of the Tian Shan, especially here in northwestern China and Xinjiang. There's been a few historic earthquakes. But then also around the north edge, there are more of these green dots, which are historic earthquakes, so pre-instrumental, so they're like pre-1960s. And it's these that I want to talk about. So this just shows the convergence from GPS across all of Asia. And you can see these velocity vectors between northwestern Tibet and the sort of stable Eurasian platform. You see the arrows change length a lot. And so that's the convergence across the Tian Shan is maybe more than 10 millimeters a year. So that's why those thrust faults are there. So this is an interesting place where there were at least 3 big earthquakes within about, 24 years. So first was this one around this is, if you know much of the geography of the region, there's the former capital city of Kazakhstan, it's called Almaty, and it's right here. So near to Almaty in 1887 was this 7.4 earthquake. And you can already see the fairly sharp topography of the mountain front, consistent with reverse faulting there. Then in 1889, 2 years later, was a really big earthquake that we don't know much about, called the Chilik earthquake, and we're still kind of studying this one, trying to find out more evidence for it. And then in 1911 was the Kebin earthquake, or Chankimen. So this is the one I'll talk about. And this little inset figure here shows the isoseismal. So this was the recording of what people felt by intensity. So the innermost one is the 9 intensity. So the blue one is Kebin. You can see it's really elongate in this valley. So we already know pretty much where the source was. But the Chilik has a much bigger 9 isoseismal. So it was probably even bigger than Kebin, just because the equivalent felt intensity was broader. But we don't know where then in this big piece of the mountain range the source was. We're still looking for the causative fault. And so this is right at kind of close to the end of the Russian Empire. And so this was on the frontier of Russia at the time. So the questions that we ask when we study this is the regional seismotectonics. How do these big earthquakes occur and accommodate that shortening? What's the description of the reverse fault behavior, the phenomena? How does the landscape record these earthquakes, and how big was this particular event? So this earthquake, because it was occurring in the southern end, the 1911 earthquake occurred in the southern part of the Russian Empire, the Tsar, the king of Russia, he sent some guys down there. He said, you guys go and see what happened. And so there was an engineer named Bogdanovich who went. And so you can see these guys riding their horses here next to these fault scarps. And so Bogdanovich, he was a good engineer, so he was just recording everything. And so he wrote a book then in 1914. And so this has a lot of the primary observations from the earthquake. And we think it was a little bit feeling competition with the Americans, because in 1908, there was a book written about the 1906 earthquake. So they wanted to have their report. So Bogdanovich mapped the rupture, and so that's shown in red. And then some French guys went then much more recently in 2001 and mapped, and their lines are this from Delvaux. So just to show what we did, my student and I, we worked and we went along the whole rupture and we remapped it with more, maybe we were able to go everywhere. And so we had more field checking than I think Delvaux. But we also measured offsets. And so we did many topographic profiles like this one in the field. So you can see just, these are the dots. So we would measure with the tape measure, the distance, and then with the compass, the angle between us. And so with angle and distance, you can make a profile. So it's simple field geology work. And so all of these measurements we made, the earthquake, well, mostly, and actually it changes. So that's one point I'll make, is that it's convergent, so it's reverse. And over here, the fault dips north. And so that means it's north side up. And so it's more of a thrust here. Then in this area, it actually is a reverse fault, so it's still dipping north, but it's much steeper. And the main trace is here. These are secondary features. And then we come down in this area, and what's interesting is right here, it dips to the south. So it flips its dip direction, which is quite interesting to us, and is an example about how these reverse faults work, that they can be very discontinuous. And so I'll show now. So what I'm going to do is do a tour from this side, from the west to the east, just doing basic description. And so this one we call Del Arik, and there's a road that comes through here. And so there were some lines we mapped, but we think it's the rupture ends somewhere around here, the 1911 rupture, because that's the end of the fresh scarps. But going this direction, there's a thrust fault at the mountain front. So the fault continues, but the earthquake stopped. So then we continue. This is called Lower Chon Kimin, and this river's called Chon Kimin, which means big valley. I think Chon is big. And so here, this is what I said. This is the south dipping part. So this side would be south side up. But right in this area, it flips and it starts to be north dipping right in here. And so that 1 to 5 meter vertical offsets. And so here's a picture of the scarps, this one coming through. And what's interesting about this is the rupture was not in the bottom of the valley, it's on the side of the valley. So the valley's closing, and the thrust fault it's really a reverse fault, it's very steep. And it's lifting kind of this mountain in the middle of the valley. And so that's shown right here. And so we saw a gap in the mapping from Bogdanovich in this area, but we think he missed it, like he didn't ride his horse up there or something, because it seems very sharp and consistent with the other scarps. So then we went to Upper Chon Kimin, and here it's a higher alpine environment, mountains, and so the geomorphic processes are very rapid, and so they erase most of the scarps. So that's why you see more discontinuous evidence of cracking. And the main trace we think is still on this side, but it's really hard to do much in here. So then it steps, and what's important to see is it steps from here over to here. So it's a big 10-kilometer step over between the end of the Chon Kimin to the end of this next segment, the Chon Aksu. And so this step over is an important break, because if you remember my lecture from Wisnowski, he said 5 kilometers was a good length, and step over is less than 5, you could expect to jump, but step over is greater than 5, should stop. But this one, it went across it. So it violates this kind of a rule. But it turns out that's common for reverse faults. They don't follow the rules as well. So here we with the student, we walked over this glacier, so we checked everything, and we could see that the displacements were larger, as much as 5 to 7 meters. And here was a place. Now this is quite a beautiful place. So let's look at the map here. So you can see our field mapping. So the river comes along like this. And again, the fault is not at the bottom of the valley, it's on the side. And it lifts up this central ridge here. So this is the reverse fault scarp right there. And so that's why this pond is here, because it dammed the flow. So the water would flow in like this, and it should go straight to the river, but it gets stuck because of the scarp. So this lake formed after that earthquake. And so we did some surveying. It's kind of an ugly map, but these are total station survey. And so you can see we surveyed, and we mapped the lake, and then we cut these profiles. So the main thing you can see especially is profile 1 clearly shows the scarp, and it's uphill facing scarp, so it stopped the lake. Or the river, the stream flowed like this in, but it got ponded against the fault scarp. So here's 4 to 8 meters of offset. You see we're trying to project it. And then here's profile 3 over here, not as big of a scarp. So here's a view looking, now we're continuing to the east. And so we just were looking at this area here. But this place, so we're on this road. So remember the horses from Bogdanovich? They were right here. So that's the scarp, but now it's 100 years later. And the scarp goes down in this line right there. That's the fault scarp. And so it's a huge 8-meter high fault scarp across the river. And the flow is from the mountains this way. So it didn't cause damming. In this case, it just made a nick point. But then the fault continues, and it goes like this. And then this is the scarp here. It's like a big tongue just sticking out. So the thrust, in this case, many cases it was, it's steep, but there it goes like flat, and it pops this tongue out. So it's a very strange geometry. And so if we keep looking, so this site, this river, so we made a topographic map of this area, and I'll just show this is what it looks like. So we just were up there on the hill. So the fault rupture came down, but this thing is the fault scarp right here. So it's really big. And here's the topographic map we made. So the dots are the survey marks from the total station. And so the river cut, this is the old terrace, T1 is high. It's about more than maybe, it's about, let's see, 2191, 2173. It's almost 20 meters up from the lower side. But we interpreted that T2 is this piece of the terrace that goes from here to there, and the T2 offset's about 10 to 12 meters vertically. And then T3 is another kind of, the terrace cuts down again, and it's about 6 to 8 meters. So we struggle to interpret is the earthquake, it lifted up the terrace and T2, and so but then did it cut down a little bit and stabilize, and then cut down some more? And so T3 is from after the earthquake, and it's just a time of stability before it cut down more? Or is the T3 to T2 the correlation for 1911 earthquake, and T2 to T2 offset would be 2 earthquakes? So 1911 plus 1 more, which would be like 6 to 8 plus another 4 to 6 to uplift. So there's some ambiguity about how to interpret this site. And what I mean is basically looking, it's a little bit hard to see. This is mostly T2 right here, to T2, but as you go right there, it's a little bit lower. So that's the T3 surface right here. I'm trying to figure out if it matches. So here, because you're asking about segmentation, so let's just look at, so Chon Aksu, this segment, and here's the dammed pond, and there's the broken river, okay? But as we come to the end, right here, just keep this spot in mind, that's the transition to the next segment, which is called Aksu segment. And here is a big step. It's not as big as the other ones, about 5 kilometer left step in the thrust. So there we could clearly segment it again. And so we changed the name. It's really nothing else. And as Suchi says, I sectioned it again. So to be more just clear that this is geometric sectioning and there's no other implication about behavior. And so in there is very complex thrust zone, no obvious strike slip in this area. But one thing we started to see, although it does say a little bit of strike slip, but we start to see these yellow lines are some secondary big cracks start to appear. And especially this line right here, you'll see in a moment. So this is called the Koch belt transfer zone. So see this thrust fault right there? That's this transition zone that I just talked about. So there's the boundary between the two sections. And in this light, you can very nicely see the thrust fault scarp, but then also these probably deformations of the old landscape due to repeated deformation in the thrusting zone. So from there, the thrust goes along and goes underneath us. So this picture's taken from maybe over here. So now we go along, we're looking actually along this main fault scarp. This is not quite right. We see the fault here, but the thrusts are now just to our right. And here it is looking straight at the fault scarp. So here's 1911 fault scarp right there. You see very nice. But you see older fault scarps above. So it's been active many times in the past. But the other thing that's impressive about this is look at this line up here. Look at it in 1911 with huge, like normal fault or landsliding in the area behind the thrust. So the way you want to think of this is the thrust is dipping away from us, right? It's right in the front of us. It's going away and down. And then several kilometers behind is this high angle structure. It's dipping toward us like a normal fault. But it's kind of a semantic question. Is it a landslide or is it a normal fault? It's a deep-seated landslide. And so we went up there. Here's that scarp. So it's a pretty big scarp. You see, Chris, so it's like 3 meters high. So it's relatively short for its length, so that implies that it didn't happen as its own little earthquake. It occurred in the 1911 earthquake as part of the deformation. So keep going. This is the same segment. It's a repeated slide. So we just were looking at this zone. So we keep going down, and we think that in this area the fault is steeper, and then as it comes out to the mountain front, it flattens, but it's still north dipping. Secondary extensional features. So here's the very end, one of the last scarps. This is now on a terrace, but out at the mountain front. And so one of the interesting other features of this earthquake was it caused some huge landslides. So this is a big earthquake-induced landslide called the Ananyevo landslide. And it was one of the places where the people were killed from the earthquake was because there was a village that was in this valley that was just completely covered by the landslide. So this is one of the things we have to watch for is sometimes in the earthquakes, it's not the faulting or the shaking that is dangerous, but it's these secondary mass movements. Here's other deformations. So this is at the coast of the lake. This big lake is called the Isikul, and you see there was some shaking, and the ground failed, and so you see the soldiers are standing on these blocks. So in our interpretation, so I'm almost to the end of this is a view. Remember my tour, so this is looking to the east, and each one of these would be one of the fault planes. So let me see, do I have a map nearby? Yeah. Here's the map. And so that view that we have in the prior pages from over here looking at the faults. And so what I'm trying to show is this is northing, so this would be south is to the right. So there's that flip in the dip. And then we see these step overs, so 10-kilometer step over and a 4-kilometer step over. So that is where I said that the Cookville step over, the one with the pretty fault stripes. And then here's the changing dip. So the middle faults are steep, and then these end faults are shallow in their dips. So we assumed something like 45 and then 60-degree dips and then 45. And so one of the things that Bogdanovich, he talked to the people and who lived there, and he said the source of the shocks registered in the populated areas was not a single localar line, but the series of lines. For example, in Almaty and at the lake, there were registered some consequent shocks following quickly one by one from the series of lines. So what we think that means is that this was a kind of a multiple bursts of seismic energy. So it broke, and then another one and another one. So maybe the rupture was coming along here, and it got stuck for a few seconds, almost stopped, and then another burst. One, then it got going, ruptured this one, then it got stuck, and then another one, and it kept going. So it was a very complex energy release with time as it ruptured across this complicated fault surface, and it may have been felt as such. So as a summary to describe how we analyze this, here's the data in the middle. So this is slip that we inferred, and we corrected the vertical offsets for dip slip. So we accounted for what we thought was the correct dip. So vertical to dip slip. And then we have the best fitting, our best value, and then the uncertainty. So you see as we go along, most of the offsets, the slips were low, a couple meters, but in that area by where the big landslide or the normal fault was, it was at maybe 10 meters of vertical there. It was huge. So it's asymmetric for one thing, quite asymmetric. And the other thing is then, this might be a little bit hard to look at, but this is, if you take the faults and they're dipping like this, so if you stand above them and you flatten them out, because it's in almost 200, no, it went 60 to 200. So it's, it's 140 kilometers long. So the rupture, if it starts here at 1 kilometer or 2 per second, it's going to take something like, 170 to 140 seconds. So maybe 1 to 2 minutes. And then what I'm trying to say from the people's reporting is that maybe it was, it was multiple sort of bursts. So it was like we're sitting here and we get one, and that's like the seismic energy from here. But then there's another one that comes, 10 or 15 seconds later, and then a third one. So it's this kind of bursting type of rupture, because it's actually, in one way you could say it's a few earthquakes that occurred one after the other. So that it's sort of a semantic point that you could say, well, it's 5 earthquakes, but they occurred along the fault over a period of 2 minutes. So therefore, because it appears that the rupture never really stopped, or at least geologically we can't tell, then we call it one single event. The total moment is, something like this, but the contribution from each of those patches is, down here. So each patch is contributing, like less than, something in the, down here below, like 10 to the 9, something like 10 to the 9. So each one of these is like a 6.8 or something, each patch. But when it adds up, then we get more energy. Okay, so this was an example just to show how we might analyze one earthquake, just very sort of in a practical sense for you. Okay, now there's maybe we can take a short break and then I'll show the general lecture of reverse faulting.